So today we'll be talking about wireless LANs. There is a standard for wireless LANs. It's the IEEE 802.11. So IEEE 802.11 specifications for wireless LANs cover the physical and data link layers. So we also, like Ethernet, we cover physical and data link layer of the protocol stack. The standard defines two types of services. So this standard, the IEEE 802.11, defines two types of services: the basic service set and the extended service set. We sometimes refer them as BSS and ESS. BSS is made of a stationary or a mobile wireless station, so these are stations, and an optional base or access point. So this is optional, not mandatory. You can have BSS as an ad hoc, so this is an ad hoc BSS without an access point. Devices can communicate without access point, or you have this infrastructure mode BSS, which contains an access point. So either an ad hoc network without a BSS, without an access point, a BSS can work in ad hoc mode without an access point, or it can work in infrastructure mode, which will have an access point. So the access point will coordinate the communication. All the devices that are associated with the access point will coordinate their communication using this access point. So this is about BSS, basic service set. As I said, the standard defines two types of services: basic service set and extended service set. In extended service set, we have two or more BSSs. So this is a BSS. This is another BSS. So we can have several BSSs. One maybe within, you see here, a BSS, another BSS, another BSS. So we have BSSs with APs. We don't have BSSs without AP in the extended service set. In this case, the BSSs are connected through a distributed system. So you have like mostly the distributed system will be using cables or copper or maybe fiber connectors. When BSSs are connected, the stations within each of one another can communicate without the use of an AP. A mobile station can belong to more than one BSS at the same time. So this mobile station can belong to this BSS or to this BSS, both of them at the same time. And the stations within each within reach of one another can communicate without the use of access point. So they can communicate without communicating or using the access point. Uh, 802.11 defines 3 types of stations based on their mobility. So based on their mobility, we can have, the station can have 3 types. Non-transition, a station with no transition or non-transition mobility is either stationary, not moving, or moving only inside a BSS. So non-transition station will either be fixed or move within this BSS, not move to the other BSS or the other BSS. So non-transition means the station either is stationary or it moves within a BSS. It does not move from this BSS to this BSS. Basic service set. If you have BSS transition, a station with BSS transition mobility can move from one BSS to another, but the movement is confined inside one ESS. So this is one ESS. You may have another ESS. So BSS mobility, this one, or BSS transition means the station can move from this BSS to this BSS, or from this BSS to this BSS, but it cannot move from this BSS to another BSS in another ESS. So the movements are confined within a single ESS. You cannot move from here to here. Okay, so a BSS transition, a station with BSS transition mobility can move from one BSS to another, but the movement is confined inside one ESS. So this is an ESS, this is an ESS. So if the station is belonging to this ESS, it can move from this BSS to this one, or from this to this. But it cannot move from this BSS to another BSS in another ESS. This, like for example, you have a mobile provider, your mobile, for example, company. You can think of Kurak, for example. Your mobile belongs to Kurak, but this is, for example, Asia Cell. You can move to, these are towers for Kurak, and these are communication towers for Asia. You can move to another city and connect with Kurak's towers in another city, but you cannot connect to towers from Asia Cell. This is like BSS mobility or transition. We also have ESS transition mobility. In ESS transition, a station with ESS transition mobility can move from one ESS to another. So we have one ESS and another ESS. So if you have ESS mobility, you can move from this to this. This like roaming, when you, for example, go to another country. So this is another one ESS, you move to another ESS, but still you can't communicate. So you can think of roaming as an example here. So in ESS mobility, you can move between ESSs. The 802.11 MAC sublayer is actually defining two MAC sublayers. We have the, you see, this is the data link layer. So we have the LLC and we have the MAC sublayer. The MAC defines two sublayers, so it's a point coordination function and distributed coordination function. Point coordination function and distributed coordination function. Distributed coordination function uses carrier sense multiple access collision avoidance access method. This is a random access method, and in this method we try to avoid collisions because, as I said, the wireless LANs cannot implement collision detection for many reasons. For these reasons, for collision detection, a station must be able to send data and receive collision signals at the same time. This can mean costly stations and increased bandwidth requirement. So you have to send data at the same time, listen to collision signals. Collision may not be detected because of the hidden station problem, which we'll explain in the coming slides. Signal fading could prevent a station at one end from hearing a collision at the other end, because, as I said, wireless signals fade very quickly when they travel. So if collision happens somewhere, some stations may not hear the collision signal because it's very weak. So there are several problems that limit the use of carrier sense multiple access collision detection. Therefore, we will opt to use collision avoidance protocol. So collision avoidance will try to prevent collisions. The protocol, this is a description of the protocol. So before sending a frame, the source station senses the medium by checking the energy level at the carrier frequency. The station uses a persistence strategy with back off until the channel is idle. So we studied these persistence strategies, the one persistence, non-persistence, and p-persistence strategy. So the station will sense the channel and use one of these three persistence strategies. After the channel is found to be idle, the station waits. It will not send immediately. It will wait for a period of time called the distributed interframe space, DIFS. So we are sensing the channel. We found it's idle. We'll wait for DIFS. Then the station sends a control frame called the request to send. Still we are not sending. We just send this RTS frame. After receiving the RTS and waiting a period of time called the short interframe space, SIFS, the destination, so this station wanted to send the frame. It sends the channel. The channel was idle. It waited for DIFS, then sent the RTS frame. The other station intended to receive that data will receive the RTS and wait after that for SIFS, short interframe space. The destination station sends a control frame called clear to send. So you wanted to communicate with this station. The station received the RTS. then it waited for this period of time, then sent this CTS, clear to send, to the channel that wanted, to the station that wanted to communicate, the source station. So we send this back to the source who sent us the RTS. The source station sends data after waiting SIFS. So again, when you receive the CTS, that when the source receives a CTS, it will not send data immediately. It will wait for SIFS, and then the destination. So the destination, after waiting SIFS, sends an acknowledgement to show that the frame has been received. So after that, you see the source waits this time and then sends data to the destination. The destination will wait for SIFS, sends an acknowledgement to show that the frame has been received. So if we look at the algorithm here, you here have a frame to send. Set a back of, as we said, we will try many times if there are collisions or there are problems sending, as in we'll set off a back off, set a back off to 0, back off to 0. We set k equals 0. Now we'll use one of the persistence strategies, like one persistence, non-persistence, or p-persistence, and check the channel. Is it idle or not? If it's idle, okay, then if the persistence strategy found that the channel was idle, for example, then you'll wait for the IFS. You'll not send data immediately. You'll wait for the IFS. Then after this time expires, you send the RTS, ready to send. And then you set up a timer and wait for the CTS. If CTS is received, okay, so you send the RTS to the station that was intended to receive the data. The station will send you the CTS, clear to send. Okay, so if you receive the clear to send, then you wait for another SIFS. Okay, then send your frame to the, set a timer, and because there's some time until you receive acknowledgement, set a timer and to wait for the acknowledgement to be received. If the acknowledgement is received before this time is out, then that means you successfully delivered the frame. If it is not received, it means there is something wrong. Then you try again. You increment your back off and try again. Of course, you check if you tried many times. If you tried many times, you may stop now and wait, try again sometime later. But if the attempts are not, for example, 15, less than 15, then you wait for back off time and then start again trying to send. If CTS is not received, then again you'll go, and because something happened, when you send the RTS, maybe it was not delivered because of some reason, because of errors, channel is bad, collisions happened, whatever reason, the CTS, if it's not received, then you try again. So this is the carrier sense multiple access collision avoidance protocol. We have the network allocation vector, which is used to achieve the collision avoidance aspect of carrier sense multiple access collision avoidance. So when a station sends an RTS frame, ready to send frame, it includes the duration of time that it needs to occupy the channel. So in this, when you hear send the RTS, you'll tell in this frame, this is a control frame, you'll tell I want this channel to be occupied, for example, for 1 second. Okay, all the other stations will hear this RTS, not the receiver, intended receiver. The other stations will also hear this, and they will know that the channel will be occupied for 1 second. Therefore, the stations that are affected by this transmission create a timer called network allocation vector, or NAV, that shows how much time must pass before these stations are allowed to check the channel for idleness. So when you hear another station hears this frame, it knows that there is going to be some communication that will take 1 second. So they will call their network allocation vector, and they will not sense the channel during this 1 second. Until this 1 second ends, then they can again sense the channel. Each time a station accesses the system and sends an RTS, other stations will call or start their network allocation vectors. Okay, so all other stations who receive the RTS will call their network allocation vectors, and they will not sense the channel and not try to send data until this time expires. There is one station that is intended by this RTS. That station, of course, will send the CTS and start the communication. So this was, we'll use this protocol for the random access method. We have also point coordination function. Okay, so we said we have the distributed coordination function, which uses carrier sense multiple access collision avoidance, and we have point coordination function. This is like a controlled access method, not a random access method. We studied the access method. We said we have random access, we have controlled access, which can be like token ring, polling, reservation. So a point coordination function is controlled access method, not random access method. Point coordination function is an optional access method that can be implemented in an infrastructure network only. You cannot implement this in ad hoc mode, only in infrastructure. That means you need access point. Okay. Why you need access point? Because this controlled access method, and the access point will manage the access. It is implemented on top of DCF and is used mostly for time-sensitive transitions. This is actually important when you have priorities and you want to serve some data at a time, like if you have multimedia data or sound packets that you want them to be sent in time and not get delayed. So you can use point coordination function. You can provide quality of service. Point coordination function has a centralized control access method, content-free polling access method. The IP performs polling for stations that are capable of being polled. The stations are polled one after another, sending any data they have to the IP. So it's a controlled access method. It uses polling. To give priority to PCF over DCF, because we want PCF to for time-sensitive data, so we give it more priority than DCF, distributed coordination function. Therefore, we use another set of interframe spaces. We call them PIFS, or point coordinated function interframe spacing, and the SIFS also there. Short interframe space. The short interframe space is the same as in DC. This is the same as we used in the distributed coordination function. This one is only available in PCF. It's shorter than this time. PIFS is shorter than DIFS. This means that if at the same time two stations wanted to communicate, and a station wants to use only DCF and an IP wants to use PCF, this timer will expire first, so the access point will have priority over the other station that uses the DCF, because this time PIFS is shorter than the other time, which is SIFS. Therefore, this time will expire first, and the access point will have access to the channel before the station that uses DCF, because its timer is longer.